I'm going to have to admit, folks, that I have to go in and look at your e-learning suggestions on songs because I've been extremely busy and have not been able to get to that. So I will have to save some of those song selections for next week or a different time or special videos. Who knows? Maybe we won't even be in school on Friday. We'll see. Been a cold and e-learning kind of week. Anyway, let's graph the blue sine wave. Who the heck did this scale here? We're gonna have to change the scale here, just for our own sanity's sake. We're gonna make that a 1, and we're gonna make this a -1, because that's ridiculous. Have this little tiny wave. Who makes these things? Oh yeah, don't mention that anymore. Okay, so the sine function, there's hk. It's on the center line on the wave, and 2 pi units later, it is repeating the pattern halfway in between. It's at the center line again, halfway in between point 1 and 2, or 1 and 3, I should say. We're up, and between 2 and 3, we are down. So, you got the basic amplitude, and that's gonna go up and down. Whoa, gee whiz, I missed it. Okay. Okay, what is going on here, folks? Maybe I should go this way, and then hopefully I won't. Gee, that was much better. All right, so when we would have another point here, a maximum point here, and it would continue the cycle and go that way. And of course, on the other side, we would be continuing the process, duplicating things over and over and over. And so on this side, we can be coming down, dipping, going up, hitting, down, and on we go with the show. Okay, so that's the sine wave, and then we can switch to the red one and do the cosine. Okay, we know that hk is not on the graph, but it's under the max. 2 pi units later, it's going to repeat the pattern halfway in between. It's going to be all the way at the bottom, and then we can find the other points in the middle there. And of course, this would be doing something like this. Yeah. Oh my dear. Who hired this guy? All right. Oh my goodness. Stop laughing at me, okay? I haven't had enough coffee. All right. I know it's evening hours and all. What is it, like 8:20 at night? I'm making this e-learning video for you guys for tomorrow. All right. Man, I think that was difficult. Now, tangent can also be defined as the sine divided by the cosine. That's the y over the x. And that makes sense because it's the slope of the line. Well, since cosine's in the bottom, we would have a problem every single time we hit cosine. Since sine is in the top, whenever 0 occurs in the top, we end up with an x-intercept. So if sine is 0 in the top, just look at the blue graph. The tangent is going to hit the x-axis every time sine does. But every time we get a 0 in the denominator, it creates an undefined situation. Well, that's going to be an asymptote. If I can spell, because I'm running out of room. Okay, there we go. So every time the red ones are hitting the x-axis, I'm getting another one of these asymptotes going on here. Doo-doo-doo. Okay. I got mail, so I better check it. And yes, I know I am male. Okay. So what happens when we graph the tangent function? Let's look at this circle. And so we just showed on the previous graph that every time we hit an odd pi over 2, we were getting, excuse me, Pop's making me belch. We were getting one of those asymptotes, and every time we hit one of the pi's, all integer values of pi, we were hitting 0. What's going on in between? Well, let's just analyze what we would get if we were at, say, negative pi over 4. What's the slope at negative pi over 4? Well, the slope at negative pi over 4, and is which negative pi over 4 on my graph is right about there, is -1, and we'll just for argument's sake, we'll leave the scale at each one of those blocks is worth 1. So that would be -1 because that's the slope of this line. We know our unit circle, so we should be able to identify that. What's going on at maybe negative pi over 3? Well, that's where we get that negative radical 3 over 3, right? We talked about the popular slopes on the unit circle, right? We had a -1, and then we had up here at negative pi over 6, we would have, oh man, I did that wrong, didn't I? And no, folks, just because I can't draw these things doesn't mean I'm drunk or anything like that. Most of you never believe that I've ever been drunk in my life, but it's true. Number 1, I'm too cheap. Alcohol is expensive. And number 2, I've never seen the point in my entire life to headaches and puking. Just doesn't make any sense to me. Don't mind some alcohols, but truthfully, I don't like the taste of most of them. So, but that stuff's expensive. I don't know how people afford it. So anyway, negative pi over 3, the one down here, that has to be steeper. That's why I knew it was wrong. And that's about negative 1.73. So, you're getting closer to -2. I think I'm a little bit, maybe I should zoom in because, my fingers are just way too big for this. If we're being honest, negative 1.73, we're going to be like right there. Maybe we should be a little bit nicer on that one. At negative pi over 4, we're at -1. And if you go on the other side, pi over 4, that's going to give you a +1. Oh, I forgot, negative pi over 6. That's, somewhere in this region. That's going to be negative radical 3 over 3, which is right around the negative 0.57. And then when you get on the other side, you got the 0.57. And you start doing the opposite, right? At positive pi over 3, we're at the 1.73 mark. And so what we should be seeing is something that's doing this. And obviously, I need to back up. Now, I know that some of you are probably going to say, well, Mr. Staley, doesn't that kind of look like a cubic function? Yeah, kind of. It's kind of got that same idea, but it's doing the same thing over here. Because every time you jump across that asymptote, you get the exact same slopes, right? All right. So we're going to have a lot of these things. Whoa. Yeah, you get the idea. We're getting closer to the asymptote. Okay. That's a pretty good looking picture. Don't do that. I almost drew all over it. Okay, let's see if we can understand things like period. How long is it taking before it repeats the pattern? Well, this is different than the sine and the cosine. This has only got a period of 1 pi. Amplitude, okay, that's the distance from the center line, which we know the center line, y equals 0. Center line to the max or the center line to the min. There is none. Right? You can't do that. Don't try to throw infinity at me. Okay? That's not a distance, for crying out loud. Anyway, so, and we also talked about how this, we just mentioned that, y equals 0. Okay? That's what the tangent function looks like. Now, we just talked a minute ago about that whole sine and cosine thing, and how the cosine wave, when you look at it, the cosine wave as it's coming through here every time, oops, stop it, every time it's hitting one of those zeros, that's creating that asymptote of the graph. So we mentioned that idea earlier. We don't need to beat that one into the ground. Okay, so the tangent function, all this cool stuff applies. Now, one thing that I do want to point out, or I'm going to point out a few things here, but I'm going to back up. I want to ask a couple questions here, which I think I did not do a good job of, but mentioning earlier. Now, we talked last semester about this idea of even and odd functions. Okay? We talked about how even functions have reflection symmetry across the y-axis. One of those examples was a parabola, you know, even function, right? Because it had reflection across y-axis. And then there was the odd, you know, we had like y equals x cubed was an example of one of those. And that was odd because it had rotation symmetry around the origin, right? Everything was spinning. You could spin it 180 degrees around the origin and it would land on top of itself. Okay? The sine wave, the blue one right there, that one goes through the origin. If you would spin that 180 degrees, it would look exactly the same. That's why the sine wave is an odd function. But if you look at the cosine one has reflection symmetry across the y-axis. Please, dark, please. You can actually reflect the red one, you know, split it right down the middle with the y-axis. So that means that the cosine function is an even function. Okay, that's something we should have mentioned, you know, talked a little bit more about when we were doing sine and cosine. So when we look at the tangent, what do you think is true? Do you think you can reflect it across the line y equals x? Can you cut it right down the middle? It looks the same on both sides? No. Can you spin the whole graph 180 degrees and make it look exactly the same? The answer is yes. So we know that this is an odd function. Okay? So tangent is an odd function. Now, another thing that I would like to point out is that the domain and range. Range is everything, right? Negative infinity to infinity. But the domain's actually weird because it skips certain values. Notice that it says all reals except, and then look right here, odd multiples of pi over 2. Odd integer, should say like odd integer multiples of pi over 2. Those are the problems. Those are the, and guess what? When we start doing horizontal stretches and shrinks, that's going to change. The vertical stretches and shrinks, you'll hardly even notice. In fact, I don't even think it's worth our time talking about vertical stretches and shrinks for tangent because there's no max and min, so it's really going to be hard to tell unless we're going to graph individual points, and that sounds like a huge waste of our time. But all this other stuff we should know. It's a continuous function, right? It's continuous on its domain, except when you have to keep picking up. It's discontinuous when you have to pick up at the individual. So when it says it's continuous on its domain, it doesn't mean the whole function, just for the parts that are in the domain. Since they exclude these values, then they can get away with saying that. Otherwise, that's, it is really, you have to pick up your pencil to continue drawing the rest of the tangent wave. So I would call it overall a discontinuous function. Each part, in between the boundaries or in between the asymptotes, it's increasing, right? Symmetric, we talked about the odd function. Not bounded above or below, that seems pretty obvious. No local, so no relative mins and maxes. Definitely no horizontal asymptotes, just the vertical ones. And you can see that these have to go together. Now they kind of have a weird notation. Vertical asymptotes are at k pi over 2 for all odd integers of k. So they're just trying to say odd integer multiples of pi over 2. That's all they're getting at. End behavior. Those limits don't exist, right? At all, because as you go to infinity, it keeps going up. Oops, sorry, that's a really bad one. Okay, it's doing that, and that, and that, and that. I mean, where in the world's the limit as you keep going to infinity? Ain't got one, folks. Let's see here. Graphing a tangent function. Describe the graph of the function. All right, so now, if you were to divide by -1 on both sides, you would see that it's the fireproof form looks... Now, what's going on inside those parentheses? We got 2x over 1, and what should we multiply the top and the bottom by? Of course, 1/2, like we've done so many times before. And that gets us 1x over 1/2. So there's my fireproof form. We can tell that there is a horizontal shrink. Wow, I can't spell. But at least I can see that I'm wrong. Shrink by 1/2. Okay, so we got a horizontal shrink by 1/2. We also have a reflection across the x-axis. Ooh. Okay, so no shifting. So my HK is still 0, 0, right? No phase shift, no vertical shift. Okay, center line of the wave is still going through here, right? All right, now, and don't get confused with that, the whole idea of like a horizontal asymptote, because that's not true. We still know that HK is there. Now, if we did a shrink by 1/2, what does that make the period of the function? Well, remember, the original tangent function is pi. We're going to multiply by the absolute value of 1/2, which makes the period pi over 2. Now, if you did a shrink by 1/2, now here I'm going to draw in the old. These are the original asymptotes. So, if we multiply those by 1/2, then I would have new asymptotes here at pi over 4 and here at negative pi over 4. What's the distance between pi over 4 and negative pi over 4? That's right, folks, pi over 2. Right, you're basically going 45 degrees in both directions. So that's a total of 90 degrees, which is what pi over 2 is. So, let me get rid of the blue ones. Slowly, step by step. Okay, so we have to have our tangent function inside here. And then How far to the right should I go to find another one? Oh, right there. You can't go more than pi over 2, because every single pi over 2 would be another one of those asymptotes, right? If you go the other direction. So, truthfully, if you can find me one, then you can graph, whole bunches of them, right? They have to go through, and, we can do this for a long time, but who really wants to? Seriously. Okay, but that's the basic idea of what's going on. What did we forget? Oh my goodness. We forgot our reflection across the x-axis. Uh-oh. Alright. Man, the viewers at home are really going to be upset with me. What's that going to do? Oh, better get rid of those arrows. Yeah. Flip. Man. Trying to rush through things and not paying attention does not pay off. Okay. Sorry about that one. Okay, cotangent. Now, cotangent is where is the reciprocal of tangent. So that would be cosine on the top and sine on the bottom. Okay, so what you see in this graph is a tangent function, right? That's basically what you're seeing. So how does cotangent relate to it? Well, it's a reciprocal. So that means everywhere where the tangent goes through 0, that becomes a vertical asymptote of the cotangent function. Okay, so as you can see, it's got a vertical asymptote at 0 and at pi and at negative pi, all the integer multiples of pi. And so so this is going to be an x-intercept, that's going to be an x-intercept, so forth and so on. When a reciprocal function is going to flip that value over, and so you're going to end up with something that looks like this. Almost reminds you of a reflection across the x-axis, but as you can see, the x-intercepts and the asymptotes are not in the same place. So that's a cotangent function, and yeah, it goes on forever and ever. There'll be another one of those x-intercepts here. It's going to continue to do. There'll be another one over there, right? And do the same thing over here. Blah, 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 blah. That's really not that hard to graph these reciprocal trig functions. They're pretty easy. Now, so remember, a reciprocal trig function, so this is 1 over sine. Okay, so here's my sine wave. I want to draw the cosecant. Every time it hits the x-axis, it's another one of these asymptotes. Something weird is going to happen on this one, though. Okay? Okay, this is 0, and this is pi, and this is 2 pi. So you can see that the period of this is going to be pi. All right? Now, what's happening in between? When you take these things and you do the reciprocal, something weird happens. You get something that comes up, touches. It's almost like it's all of these things that are coming down, touch and leave. Okay? Not like parabolas, but kind of, I kind of understand what your thought process is there. You got all these shapes. They touch. So if you know what a sine function is, it's pretty easy to tell what a cosecant function looks like. Now, does it have weird stuff like what's your domain? Well, your domain would be everything except the odd. So domain, all reals except integer multiples of pi. What's your range? Well, this is where it kind of gets weird, because you've got everything from 1 up and from -1 down. So you actually have a split range, like negative infinity, right? That's way down here on the graph to positive infinity way up on the top. So negative infinity goes to 1, bracket, union, bracket, 1 to infinity. And yes, they do have to be brackets because they actually touch those spots. When you take 1 and take its reciprocal, you get 1. So that's why it has to be like that. Okay? Secant. Okay? Secant goes with cosine, right? That's 1 over the cosine wave. And that cosine wave, every single time it hits the x-axis, guess what? Another one of those vertical asymptotes. Because of that whole reciprocal idea. And just like we talked about earlier, right? It's got to come up, hit it, leave. Come down, hit it, leave. Come up, hit it, leave. All right? Yeah, so you're going to see over here on this side, you're only going to see like half of one, and over here you're going to see half of one. But we know that the other part's over there, and there's another asymptote. Same thing on the other side. It's going up, and there's another asymptote. Okay? In between here, right, from the here to here, the period is only pi. Once again, domain, all reals except integer, ooh, wait a sec, let's check, except odd integer multiples of pi over 2. Kind of like your tangent, right? And then the range is that split thing again, right? From negative, ooh, what am I doing? Come on, get serious about this. Negative infinity to 1, bracket, union. Ooh, man, you're going too fast. You got to slow down. You got to slow down. Yes, okay, so we end up with that. Okay, whoa, man, lots of cool stuff in this video. I'm going to guess that you're going to have to watch the rest of these notes over the weekend, right? So you can be ready for Monday. Okay, so graphing a cotangent function, we can put this thing in fireproof form, right? Y minus 1 over 3 equals the cotangent of x over 2. We can see that there's been a horizontal stretch. So the period by 2, so that means that the period, instead of being just 1 pi, gets stretched, and now it is 2 pi. Okay? So if the original asymptotes were at 0 and pi, now if by stretching those, now 0's not going to change, right? But the asymptote will go over to 2 pi. Likewise, you'll have another one over here at negative 2 pi. Now, we have also shifted this thing up 1 unit. Up 1 unit. So that means we've got the center line of the wave running right through here. Maybe I should just do a solid line. Okay, now, the whole idea of stretching it by 3 over here on the vertical, really hard to tell. Really hard to tell. Now, I know it's going to go through that point right there, and it's going to go through that point right there. And the cosine wave, nothing's been reflected, so it's going to do that and that kind of thing like there. So it's just your basic your cotangent, right? If we go back and look at the previous tangent graph, which was right here, the red one, and all we're doing is doing a horizontal stretch. Okay, sorry, that was in both directions accidentally. So there is your Horizontal stretch. Don't get wrapped up on this this idea of the vertical stretch, because truthfully, all you're doing is you know you're going to make it go up like this and down like this, but unless I'm going to graph individual points, I'm not going to get all bent out of shape about that. I would care more that the person understood the period, where the asymptotes were, and the basic shape. That would make more of a difference to me. And I think that's enough for now. Have a great e-learning day.